Okay, my kitten got in here, so this is going to be very interesting at the least. Um, so let's go over the problems, the practice problems I gave. The first one has to do with a dihybrid cross. And you have big B, little b, big S, little s, big B, cross with big B, little b. Oh, let's just little s, cross with big B, little b, big S, little s. Now, you should know from doing Punnett squares, when you are heterozygous in all four positions, your phenotypic, your PER is always a 9-3-3-1 ratio. That means out of 16 squares, 9/16 will be dominant, 3/16 will be one dominant, one recessive trait. The other 3/16 would be one recessive, one dominant. So these are your recombinants, where they have one dominant, one recessive. And then the last group are your homozygous recessive. So they have both recessive groups. So I ask you to figure out the observed, and I gave you the observed, and you have to figure out your expected. To figure out your expected, what you would do is take how many that you got. We got 1,191, and you would take that number and multiply it by each one of these ratios. So I would expect out of 1,191 of these corn kernels to be 9/16 of them to be double dominant. So I take 9 divided by 16 equals, and then multiply by 1,191, and that gives me, so that expected would be 669.9. So you could round to 670, and I am gonna write that in. So that would be 670. And then you would take your 3 divided by 16 and then multiply that by 1,191. And that gives you, and these are the same, right? You're multiplying the same thing. So those are both going to be 220. Let's just, and 23. 223. And then the last one, you're going to take your 1/16. So 1 divided by 16 times 1,191, and that equals, so 74. And hopefully those numbers should be pretty darn close. 670 plus 223 plus 223 plus 74. I'm off by 1, and that's, again, just a rounding factor. I mean, if you wanted to go back in and put points or whatever, but it's close enough. Okay. So, and then you would simply do the math. And with the math, again, you remember you're going to go all the way, I'd go all the way across your column, and then you get your chi-square value. Now your chi-square value, let me just do that math. I'm gonna pause this for a second and then do the math real fast. And so let me see. Pause. Okay, so I did all my plugging and chugging, and in my last column I got 1.4. So I got 1.4. I got 1.97, and things looked really good until this one. 27.2, and then 8. And then when I added them all up, because that's what you do in the bottom, is you add them, you add the whole column up, and I got 30.12 as my calculated, my chi-square calculated. That is a huge number. So what does that mean? That means that my chi-square value is rather high. And so when you go to your chi-square chart, you're going to look up your probability of 0.05. And then you have to figure your n. Your n is your degrees of freedom. Oh, and my kitty just erased everything. Oh, bad kitty. All right, my degrees of freedom. So again, my calculated chi-square was 30. My degrees of freedom, n equals the number of outcomes minus 1. So I have 4 outcomes. I have black and smooth, yellow and smooth, black and wrinkled, and yellow and wrinkled. So I have 4 possible outcomes minus 1. So my n equals 3. And when I look up in my chart with my probability of 0.05, that means my allowable, what I will allow, what kind of wiggle room for probability will I allow? My allowable chi-square equals 7.816. And we are definitely bigger than that. So what that means is that our hypothesis is not correct. This is not the correct cross to get this outcome. So something's going on. Maybe the genes are linked, and so they're not independently assorting. Maybe there was an error in counting. Something is not right. Okay, that is what that is telling you. So chi-square values tell you whether your hypothesis is correct or not. This situation would be what we call a null hypothesis. It's not true. Okay. Now, some of these other problems I know we kind of did together, but I have other students who picked these up, so I'm going to go through them all. So if you do problem number one it is in Hardy-Weinberg. Okay, but it says practice problems Hardy-Weinberg equation. But in the first one, it doesn't give you your P's or Q's, and so you cannot. And it also doesn't say for each group, you know, that it is in Hardy-Weinberg. And when it's not, when they're giving you these numbers, what I always do is I go, all right, 94 people are big A, 300 are big A, little a, and 15 are little a. So then I add them up. That means I have 409 people in my population. Individuals. Okay. It said, what's the frequency of the allele for unattached earlobe? So it's asking you, what is your big A? How many big A's do you have in this population? Yeah, that was my kid. So I may be kicking her out soon. So I'm going to calculate that up. So big A equals 94 plus 94 plus 300, right? We have each person here has 2 copies of the big A, and my heterozygous only has 1 copy. And so that gives me 488. Now these are alleles. This is individual. So for me to get the alleles, I got to times that by 2, because this is not a frequency. That's just a number. So I'm going to go 409 times 2. So I have a total of 818 alleles in my population. So I'm going to take 488 divided by 818. And that gives me, it's about 50, I'm going to go around 60%. My little a would be 300, right? My heterozygous each have 1 copy, plus 15, that equals 330 divided by 818. So that gives me 0.40 or 40%. So 60-40. Okay. So this would give me my answer for little letter A. This would give me my answer for B. For C, it asks the frequency of each of these genotypes. So C would be 94 divided by 409 individuals. So that would be 23%. And then D asked me the homozygous recessive. So that would be 15 divided by 409. And that gives me 3.6%. And E asked me the heterozygous. So that's 300 over 409. So that would be that would be 73%. Okay, so that's how I would have done that problem. Problem number 2 is the same way. So for number 2, again, I would set it up. I'd write it out. 32 people are homozygous dominant. 54 are heterozygous. 38 is homozygous recessive. So what is the allele? What's the frequency of the dominant allele? So again, my big A. So this is asking me for question A. Equals 32 plus 32 plus 54, which equals, oh, first I want to add up how many I have here. 32 plus 54 plus 38 gives me 124 individuals. And each person has 2 alleles. We have a total of 248 alleles. So I'm going to take 32 times 2 plus 54. That's 118 divided by 248. So I have 48%. And then for B, they want to know the little a. So that's going to be 54 plus 38 plus 38. That's 130 over 248. That's going to be 52%. C, ask me homozygous dominant, right? This one. So 32 individuals out of 124. That gives me 25. Actually 26, around 26%. And D asked me the frequency of the homozygous recessive. So 38 over 124. That is 31%. And E equals the heterozygous. So that's 54 over 124. And so that's 40, about 44. Hopefully I'm pretty close to being with rounding about 100%. Okay. So for the next question, they ask 3, they actually give you your P's and Q's. So your dominant would be your P equals 0.6. Well, we know P plus Q equals 1. So if P is 0.6, Q is 0.4, they want to know the frequency. So A is asking me the frequency of the dominant trait. So that is right here. So let's just do this. That's A, right? That's B. Dominant, recessive. And then C is asking, what's the frequency of the homozygous dominant genotype? So I'm looking for big A, or P squared. So I just have to take P, which is 0.6, and square it. And that's going to be, it should be 36. Decimals always throw me off. 36%. D, frequency of the homozygous recessive, that's little a, or Q squared. So that is 0.4 times 0.4, which is going to give me 16%. And then E is asking me for my heterozygous, which is 2PQ. So 2 times P times Q. And that's going to be, I think, let's see, 2 times 0.6 times 0.4. Yep, that's what I thought, 48%. And that one's done. Okay. And then for problem 4, it gives you again, it asks you what's the frequency of the dominant trait. Well, they already gave you that. They gave you that P is 0.7. B then means Q is going to be 0.3. And you're basically doing the same thing again. So C is asking you A or P squared. So that's going to be 0.7 times 0.7, which is 49%. Little a or Q squared is going to be 0.3 times 0.3, which is going to be 9%. And then E is our heterozygous or 2PQ. Times 2, which would be 0.7 times 0.3, which is 21 times 2, which is 42%. Yep, 100%. I just wanted to double check that. Number 5 is kind of a challenge problem. It's not something I would ask. I don't know if they'd ask you on or your AP test, but they're saying that the recessive trait for attached earlobes is lethal. So you have 200 people. 75 people are homozygous dominant. 100 are heterozygous. And 25 are homozygous recessive. So we have 200 individuals. Okay. So what is the initial frequency of the recessive allele? So our initial frequency would be of A is going to be 100 plus 25 plus 25, which is 150 over, right? We times 2, 400. So 150 divided by 400. Ooh, that is not typed in right. Just try divided. And that's going to give me, so A is going to equal 0.375. All right. And then it asks for the dominant. 75 plus 75 plus 100. So that's going to be 150, 250 over 400. So A equals 250 divided by 400. And that is 0.625. Okay. And then C is asking you what's the frequency of the initial dominant group. Okay, which this one's actually pretty easy because they're not asking you, you're missing E. So C is just an initial dominant group. So your dominant group, big A, would be 75 out of 200 individuals. And so that is 0.375. And then D is asking you the homozygous. That should be a quarter, 24, 8 and an eighth, actually. Let's see. 0.125. Okay, that's all that's asking you. It could ask you, well, what is after these guys die out? What are the frequencies? But that's that. It probably is a little bit more advanced, and I don't know if they're going to ask you that on your AP test. So we're just going to leave it at that. That is the last problem on the review packet. So the main thing that I will tell you right now on your test is I'm going to give you a problem that has to do with incomplete dominance, and I'm going to give you numbers for that incomplete dominance, and that has to do with flower color. I'm going to give you the red, the white, and the pink, if I recall correctly. I'm going to give you their numbers. You're going to need to figure out their expected. You're going to have to figure out if they are following the correct hypothesis for what your phenotypic ratio should be. All right, this test is actually pretty long as well. It might take us 2 days to complete it, and we'll see when you guys get started. So I will talk about that more on Monday. So good luck studying this weekend. And if you do have any questions, please feel free to send me an email and I will try to answer them as soon as possible. All right, good luck studying. Bye.